And again, feel free to interrupt. Yeah.
Okay, let's see if everyone's here because still unsure if Sarah, Yuri, or Dirk are here.
Yes, I know that Dirk had to go somewhere and he would listen it through his phone.
Okay,
so
I see him
while going, he has to go in Harlem, I think.
I see it. I see it. Okay, good. Then I will start. Okay, so I will give also a presentation during this workshop, but this is about the Moller-Plesset Adiabatic connection and some cases we have looked at, but also new stuff we are doing with Stefan currently, and also what we will do in the future with Arthur. So this is the content. I will not go over this fully, but the main results is that we are going to talk about the hydrogen atom. Then we're going to generalize these results as we have done in the paper, and then move on to the interpolation schemes that we have obtained already and look at the GAs of the Moller-Plesset Adiabatic connection. So the theory will be split into two parts because we first need to understand why we are looking at the hydrogen atom as a system, and then we will talk about this adiabatic connection more in detail. So the hydrogen atom is still very interesting to study because, for example, Young and Cohen and Mori Sanchez showed that just looking at a hydrogen atom, you can look at the fractional spin system where you have a half spin up and a half spin down, which you get in the restricted Hartree-Fock case when you increase the bond length to infinity and look at one locally. The energy that DFT functionals, but also Hartree-Fock give is exactly equal to the static correlation energy, as you can see here on the right-hand side. So you can just look at the hydrogen atom with a fractional spin to understand what the static correlation energy error is. And in this picture, you can also see the two systems that we will look at for the hydrogen atom. The first one is the SS1 system, which is just the one with either spin up or spin down. And the other one is this restricted Hartree-Fock hydrogen atom with half spin up and a half spin down. And this is what we call SS and half, which will come back later. So moving on, we have the DFT adiabatic connection, which I think most of you are familiar with. But the main difference between the two, the DFT one and the Hartree-Fock or Moller-Plesset one, is that in DFT, you have this density constraint that Mike already mentioned, which means that the external potential must be dependent on lambda, which is in the case in the Hartree-Fock case, where you have this independent Hartree-Fock potential, which just depends on the J and the K. Because you now also have this lambda in front of this Hartree-Fock potential, you have some different correction terms here, but the rest is very familiar between the two, only you have here the Moller-Plesset expansion, but you have the same order in the large lambda expansion as well as the small lambda expansion.
Just to make the connection with what Hugh has just presented. Most of the time, for traditions, we look at at the derivative with respect to lambda of the energy instead of the energy. So this yes. W is the derivative. Yeah.
Yes. Okay. So in the DFT adiabatic connection, we can calculate exchange correlation energy using this integral. Or in the other way around, you can take the derivative to get the W lambda. And you get these kind of plots if you calculate it for all lambda, but this is of course similar to calculating the Schrödinger equation for all these lambdas. So it's not really efficient, but we are trying to find interpolations, these purple lines, to get a better approximation of it using ingredients from both the small lambda limit and the large lambda limit. For example, what Mike already mentions, the ISI functional, interpolation strength interpolation, interaction strength interpolation is one of them. And we also want to have some of the for the Hartree-Fock adiabatic connection.
So, sorry, Tim, just one interruption about what Paula said, that the derivative with respect to lambda is for the Moller-Plesset adiabatic connection, because in DFT, actually the W lambda is a bit different than the derivative with respect to lambda.
Okay.
Well, it is the derivative with respect to lambda of the
energy along the adiabatic connection Hamiltonian, essentially. Yes.
No, I think because there is the external potential, which is lambda dependent, and you are excluding it. So I disagree.
Yeah, but yeah, okay, but in the end it cancels out when, so yeah, if you want. Okay, yeah.
But the DFT adiabatic connection is just exactly. So we can move on. So a big difference between the two is that the DFT adiabatic connection is assumed to be always convex, or at least piecewise convex, which if you've seen, for example, in the plots you can see here, where we have here a convex function. But this isn't the case in the Hartree-Fock adiabatic connection because it needs to change from a concave due to the underestimation of MP2 at small lambdas to a convex function, because that was proven in the large lambda limit to be the case. So we need to have this change from concave to convex curves. And for an example, you can look at one of our results, as you can see here, for the S-half system, where you can clearly see that we start with a concave curve here, and eventually we get at larger lambdas this convex function. So this is a very important difference, which means that some of our interpolation schemes will not work that we have used in DFT. Moving on, we can now go to the hydrogen atom. It's an interesting case to look at because we can write the Hamiltonian in the following way, which is very similar to what you had, except that we have this factor S in front of here. But this is the Hamiltonian. And when we look at this S, we can again look at this picture where we have this fractional spin systems of Wei-Young. And for the SS1 system, we have again that is just one spin up or one spin down on the hydrogen atom. And as S1/2, you have a fractional spin half up and half down, which is this system, which is what you get if you do a restricted Hartree-Fock calculation. Increase the bond length to infinity, and you will get 1/2 on both of them, and you look at one of them locally. So that's what we have done. And the equations that we need to solve is like this. And what we do is we have the J defined as this, and the K defined as this, where we have these orbitals are the Hartree-Fock orbitals, which you can get from a self-consistent calculation at lambda is 0. So for SS1, this self-consistent calculation gives you just the 1s orbital from normal Hartree-Fock theory, and for SS1/2, you have this factor here in front of the K, which means that you cannot get it very easily in analytic, so you need to use an STO expansion. And these orbitals will be slightly more diffuse, as you can see here, because the K now has less interaction and cannot remove the full unphysical self-interaction that the J has. So therefore, the electrons will be further away from the nucleus because they feel it's itself more, and therefore it will be slightly more diffuse. So how we calculate these W lambdas is by taking the energy derivative at lambda and adding this constant in front of this. And this is from the Hellman-Feynman theory. So that is how we can calculate this W lambdas very easily without having to take the wave function and calculating the expectation values. So we have used to equations or linear equations that you can solve without having to do it self-consistently. We use in either a basis set expansion, which is in our case the STO expansion, or we use an iterative fixed point scheme that was made by Siad, which we also wanted to test for this because it depends on the initial guess and also has a fast convergence, and has shown with the work of Yuri, for example, it's a really good method. And it's also block diagonal on L, so we can just look at all the different L channels separately, and we don't have to look at all of them. So we will only look at the lowest two, which are LS0 and LS1. So these are the first results for the SS1 system. You can see that both methods clearly overlap. So the base set expansion is well converged, as is the other one. And you can see that there happens something interestingly, and that's that there are two switches. You first go from the LS0 channel, and at a certain point, because it stays constant, it will eventually go to this LS1 channel, and then switches back to the LS0 channel, as you can see here. And this is very interesting, but this also creates some discontinuities. And if we take the derivative, we will get them. So what we will see here is we stay constant when we stay at the -½ energy, which you get from the normal 1s orbital. Then you switch to the LS1 channel, so you get this discontinuity. And then for the second change of states, crossing of states, you get again this discontinuity in the derivative. So you get this very strange graph, which is not really that nice for us, especially. So we wanted to look at a different system. There, the S1/2 system comes in, but first we need to look at the wave function for these three different distant states. The first one is, of course, the small lambdas, where it stays relatively constant. So this one is the normal 1s orbital in blue. But then when you increase lambda, where you go to the LS1 channel, you see this wave function with the node at 0. And when you go to even higher lambdas, where you go back to the LS0 channel, you get this green wave function, which also contains a node. And this was not what we expected. So we want to look at it later, why it does exist.
Tim, may
Yes.
I interrupt now?
Yes, sorry.
Sorry, no, just I want to make sure I understand the setup of your calculation. So so your hydrogen atom, your basis set is a linear combination of Slater functions, right?
Yes.
And so you take are there only S functions? Or so
yes.
you take the 1s, 2s, 3s, and so on?
Yes.
So you don't need to use like different m values, I guess.
No, we don't use them.
Okay, and so when you do a calculation on your fractional spin hydrogen atom, do you allow the orbitals to break the spin symmetry or not? Do you have a different orbital for the spin up and spin down electron?
Nope. We just use the same SDO expansion as we.
Right.
use.
Okay. So you have a restricted orbital, which is the same for the two electrons. Do you think it would be possible to break the spin symmetry?
Sorry, Tito. There's only one electron.
Yes.
Well, there is only one electron. That's not quite true, because there is a fractional spin up and a fractional spin down. So there is not.
There's two half electrons.
Yes.
Yeah.
So it's not really.
I mean the other one.
So I think you could break the spin symmetry.
If it wants to break.
Yeah, if it wants to break.
Yes, yes. So this is the so this you do restricted. So you are already forcing the two.
That's right.
Two orbitals to be the same. It's all restricted, and then so he did it in two ways: this STO expansion, but also just on a grid. This spectral renormalization is just solving the differential equation on a grid, right. Because yeah. So it's also done on a grid, but as you see, it's they agree. And yes, so in the L0 you have only S function, the L1 is the P functions and so on, but they don't couple, they are uncoupled, yeah.
Okay, I see. So you still have P function in there.
Yeah, the L1 is because if you write the Hamiltonian, it decouples exactly in the different L channels, yeah.
And so is your wave function fully symmetric even in the L channel, or there is a particular direction which is picked by the electron?
You mean the dependence on M?
Yes.
No, the energy is independent of M. Yes.
Right.
Because both the R3, so because what you have the R3, which is spherical, and the K, which is also generated by a spherical orbital. So in the end, it depends only on L. Yes. Yeah.
Yes. Okay. 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 And well, no, I think that's it for now. So, yeah, no, just a small last question, Tim, and after I leave you, you alone. So how do you get this expression for the R3 Hamiltonian? That I'm interested to know how you get this little s in front of k. So what is your ansatz for your wave function?
what we started with, if I recall correctly, was that we looked at a hydrogen molecule with, and then we did an expansion and looked at it locally for just one of the hydrogen atoms. And then you saw, if you worked that out, in the end, you saw that due to the spins that you need to include, because you have, if you look at a hydrogen atom in restrictor hard-fork, you have an alpha and a beta, and eventually you get a factor in 1/2 in front of it, and that's where the S comes from.
I see. Okay, because when you look at the paper of Weitao-Yang, so he's probably using an ensemble for generating his graph, which means that he must consider an ensemble of two states. One state is a spin up hydrogen, one state is the spin down, and you can couple those two states with a weight which goes from 0 to 1. Okay, and so normally you can do this by writing down like the density matrix as a linear combination of the two density matrices. And so you can't do that on the wave function, but you can do that on the densities. And after you can write down the J and K as functions of the one electron density matrices, I guess. And you should end up with an expression which looks like this, right?
Yes, I think
Yes.
this is also how we did it in the end. Yes. So I mean, you have the density matrix for the full system, which is a pure state.
Yes.
And then you essentially integrate the what is out,
right,
what is on B. Yes.
I see.
So you have an ensemble on the spin part indeed. So the
Yeah.
spin part, which is not here because we already eliminated with the S, would look like 1/2 alpha alpha plus beta beta. Yeah.
Okay. Okay. And so in the case of the hydrogen atom, so you have only one molecular orbital. So the J11 and the K11 will be the same value. So can't you actually factorize J and K and have just like a 1 plus S factor in front of it? Or is it not as simple as
No, because J and K are the same only when they act on the ground state orbital.
Yeah, on
Right.
the hard-fork orbital.
Right.
The very moment the K and J interact on any other orbital, they are not the same.
I see.
Yeah,
Okay.
because if you look here,
If you look here, yeah.
Yeah, only if this psi here is the same as this
Yeah, I see. Okay.
one, they will be the same. But if K works on another, you have this overlap function, which is different from what you have in the J. So it's not the same.
Okay. Okay.
And this one you obtain by using self-consistent calculating at the start, at lambda is 0. And then you find this wave function for every different lambda. So they will only be the same, and which is in this case only here between 0 and 2.3, where it will be a straight line, because then, and it's the same as what we had here. If you look at this equation, it's what Hugh said as well. If you have lambda between 0 and 1, this term will be positive, and this term, is still positive. So here, J and K, the best it can do is when they are the same. So it will just give the ground state the 1s orbital, and this will be the same, and they cancel.
So T2, what you're suggesting would be to re-optimize the orbitals at each lambda value, wouldn't it? So the point you're saying there is that the J and K are built at lambda equals 0, and then you're optimizing the energy using those operators. But what we've often thought before is when lambda is defining the Hartree-Fock approximation, and then J and K will become equivalent if you've got to the optimal solution.
Yes.
Which is how we've thought about it.
Yeah.
Okay.
But only when
you're self-consistent.
Yeah. Okay.
Yeah.
Yes. So as long as lambda is less than 1, yes, I agree. They would want to be the same. Well, not for S1/2, right?
Yes.
For S1/2 even.
Yeah,
Right,
S1/2.
yeah, S1/2 is not flat. Yeah.
Only at lambda is 1. They will be the same, because then this term will just cancel, and you have just the normal one as orbital, but it's only at that value.
Okay. Thanks.
So we have seen that the wave functions at larger lambda has this node, and which we will look at later. But now let's look at the results of the SS1/2 system. And here you can see that firstly, that there is no crossing of states between the LS0 channel, which are these red and blue ones, and the LS1 channel, which are the yellow and green ones. You can also see that due to that K cannot remove all the effects of the J, because there is now this S1/2 in front of it. You can see that it will not be a straight line at the start and then start decreasing. It will just be one fluid line. So if we take the derivative of the LS0 channel, we will again see this curve that we have seen before, where you can see that we have this concave curve at the start due to MP2, and eventually we will become a convex function at larger lambdas. So this also happens close to the jump of the SS1 system. So maybe that's why we couldn't see the change from concave to convex due to the discontinuities. But with this SS1/2 system, we can now clearly observe what we had expected. And if you look again at the wave function, you see again for all the lambdas, large lambdas, we can see this node starting to appear, but also we can see that the wave functions start to contract, and that it seems to become a delta function. However, the nodes increases and also stays there, even when we go closer to the nucleus. So we then looked at the normal H2 molecule, and we looked at what Stefan did for the H2 atom and then increasing the bond length in a restricted Hartree-Fock calculation. And when we increase the bond length, you would expect his results to become twice our results, because we are only looking at the R to infinity limit, which is the blue line here. You can see when he increases the bond length of its H2 molecule, it seems to become very close to our results. And even though R is 10, doesn't seem to go to our results, if we increase the lambdas, eventually it will also converge to the line, the blue line we have here. So we now know that our results are correct, and that our limit was correct, and also that the same can be observed for the H2 molecule. So now let's look at the large lambda limit in the hydrogen atom, where we need to write down the full Euler-Quantz equation, which is a bit long, but it just consists that all the normal terms, the kinetic energy, external potential, the J and the K, and where we will use this scaled variable and also introduce this cusp condition, which will become important later on when we write the Hartree potential and the Hartree orbitals, because this term that starts to become here, which is lambda to the power -3/4, and also this term lambda to the power -1/4, as well as this external potential, will diverge at 0, and this will give us a new term which has the power lambda 3/4, which doesn't exist in the expansion of the DFT adiabatic connection. However, that's maybe a few slides further, so we will not mention it until later. So what we can do is we can look at the first order, and this is just a constant that only depends on the Hartree potential and energy, as you can see here. And this can be understood in the following way. We can plot the Hartree energy, and then the electron will become at the minimizing position at the origin and will just stay in the bottom of this well. So this is the first order term, but then we can look at a second order term, which we can obtain the following equation from. It looks again a bit ugly, but it has again the same terms as always, the kinetic energy, the J and the K. And if you use this scaling coordinates, this P, which also contains now the square root of this Hartree-Fock orbitals at 0, and use this scaled energy, and use the 3D isotropic harmonic oscillator basis set to solve this equation. By using a base expansion, we can find an analytical solution, which looks like this, and which contains the first excited state and the ground state of this basis set expansion. So it's just a combination of two sets with this analytic energy. And if we now also look at it for the SS1/2 system, we do not get this analytical energy, only for very strange values of S, which don't make any sense. However, we can get well-converged results also for the SS1/2 system, which gives the following energy. And if we then look at our results together, we can see that we have this large lambda expansion, which looks like this, which has now this 3/4 term, which doesn't exist in DFT. And we can calculate these expansion constants in the following way, where we have now removed the scaled coordinates so that we get this square root of the density back, but also these constants. And we also have this 3/4 term at the nucleus, which looks like this, which does not exist in DFT. So you might wonder, how good is this large lambda expansion? So let's plot these ones for both systems and compare it to the accurate details, and what we get are these curves. So in the blue line, you can see the large lambda expansion for the first 3 constants, and then also for the first 2 or the orders, which is in yellow. And you can see that the one in yellow is much above the exact curve, which are the green dots, but also the blue ones completely overlap with the green ones. You can see in both systems for large lambda especially, but also for more lesser values of lambda, you can see that the green one overlaps almost perfectly with the blue one, seeing that this expansion works really well. And another thing is that the third order term seems to be very important for at least the hydrogen atom, but we are unsure for larger systems how important the term is, and we will still need to look at it. But it seems that this term really increases the accuracy of this expansion really well.
Tim, do we have a clue how accurate, how reliable the spectral renormalization, the green values are? Can they be considered accurate, exact, or?
I think they can be considered accurate because they overlapped really well with the SDO, and also if you look, because everything is variational, it always gave the lowest energy compared to any methods, and they were well converged. So I think they are relatively accurate.
It seems that for lambda beyond 20, greater than 20 or so, the blue curve almost reproduces the exact. So this expansion seems to converge very, very fastly, right?
Yes.
Because there might be higher order terms, but today, of course, they die out at large lambda. But
so do you have more terms than the 3/4 one, or?
I guess there are, but it's an expansion. But we don't have them.
I've tried to look at the next order term, and I think I found a value, but I've not really plotted it yet. I will need to look at it. I think you can calculate it because, for example, the 3/4 one can be calculated as the first order correction of the wave function we find for 1/2 on the equation of the 1/4 one. So you can calculate it that way, but the other one, it will be a bit harder because you cannot use the 2n+1 rule.
But looking at this plot, it seems that the 3/4 term completely does the job almost, right?
Yes, but only for hydrogen.
Okay, that's a very simple system, of course. Just it's like.
So if your green curve is almost exact, I can give you a trick to get numerically the other terms. So what you can, if you know the expansion and the power of expansion, what you can do is you can try to fit your green curve to reproduce your expansion.
Oh, yes. So I mean, imposing the first 3 and then.
So you impose the first 3 that you know for sure.
Yeah.
And you try to find so you expand the green curve in the same power, and you try to find the fitting coefficient for the very same power. And so normally in Mathematica it works very well. I've done it for a small system, and you can get like 3 or 4 terms like this, no problem.
Yeah. And one could also see which ones are 0.
Yes, as well.
So 1 over lambda, and 1 over lambda to the 5/4, and so on. I don't know.
Yes. Okay, I will look at it. It seems very interesting.
So I had a very, very similar expansion like yours, and it was exactly the same behavior. The first 2 or 3 terms were very accurate, but the 4th and the 5th and the 6th, they were horrible. So it really looks like an asymptotic expansion, really. And so you don't really know if it's going to converge or not.
Okay, good. I will take a look at it. Thank you. So now we can also try to explain the nodes. And this we can do by thinking about what happens when we go to lambda and to infinity. And what we have seen is that when lambda goes to infinity, the square of the wave function will become a delta function centered at the minimizing position, because the j is the only term that counts in the lambda to infinity limit. So for the first order term, so the electron will just become at a minimum of this minimum.
Tim, excuse me, this is related to my earlier question in Hugh's talk about 3/4 of an hour ago. We have lambda in front of a potential energy term, but the kinetic energy is lambda free. That's why when lambda goes to infinity, potential energy is made more and more important. So we are leading quantum mechanics in favor of classical. So that's why for large lambda, the electron is trying to do what it would do classically. It would find the minimum position in the potential energy without ignoring the quantum mechanic kinetic energy, the 0-point energy. Right?
Yes.
All right. That's why the wave function becomes a delta function in that limit.
Yes.
It's a very simple picture.
Yes. And this is because the leading order is this constant, we will get this delta function, but another thing that will happen, because it's linear, it will not say which representation of the delta function we will get. It will just say we need a delta function at the minimum, but that could be a lot of different ones. So the nodes and which representation of delta function must come from the second order term. So that's what we can look at it now. And we know that a node always increases the kinetic energy, but in our case, we can also see that it decreases the k. So if you look at the equation, we will only look at the k parts now and look at what does a node do to this equation. So writing this term down again, using scaled coordinates again, you get the following two integrals of the k. And what you will see is that this second integral is always necessarily 0. Because if p goes to infinity, because lambda goes to infinity, you get the following function from integral from infinity to infinity, which will be 0. So the second term will always be gone. So the condition that causes our nodes must be the first integral between 0 to infinity from dq like this. And here we can immediately see that we need to have a node because u needs to change sign. So this is exactly what we will have. And this is also exactly what we can get if we plot it for the IOH using the scaled coordinates p, which for a reminder is this scaled coordinates. And you can see that if we increase lambda, they will eventually go to the exact IOH expansion, which is just the first excited state plus the ground state for this one. So this is an explanation of the node. So it wants to remove one of the integrals of the k because the k decreases the energy.
IHO is isotropic harmonic oscillator, right?
Yes. In this case, this is an analytical function, which is the.
Yeah.
Yes.
It's just the minimum of the potential energy.
Yes.
Did you
So
calculate
now,
k separately for each of these lambdas? Or
what?
did you calculate the value for k separately for each of these orbitals just to see how close it is to 0?
No. I think Paula did it for some calculations. He looked at it, but I'm not sure. But
yeah. No, I checked that the condition was satisfied. That the integral was 0. Yes.
okay, so now we can move on to the generalization. We want to do it for larger systems, and we first need to look at the first order term, but this was already done in the first paper by Mike and Sarah and Stefan, which is the following one, which has this electrostatic potential plus the exchange energy, where this electrostatic energy is the minimization over the sum of the electron-electron interactions minus the Hartree potential plus the Hartree energy, where you can think of the first term as the electron-electron repulsion, the second term as the nucleus electron interaction, and the U can be think of about as the background interaction or the nuclear repulsion. This is just a classical minimization strategy, and what you will get, for example, for helium, you get this graph where the electrons will be not at the bottom because they have a repulsion, they will be slightly higher on opposite sides symmetrically. However, what we have found in the work of Arthur has done, if you decrease the nuclear charge, so from Z is 2 to Z is 1, but keep 2 electrons, eventually at roughly between Z is 1.1 and 1.2, it will be an asymmetric minimum. So one electron tries to move to the nucleus, but the other one goes a lot higher. But this is still the lowest energy, because in DFT, all these minimums are degenerate due to the condition that the density needs to be exact. But in Hartree-Fock, this isn't the case. So for other systems, so we have this strange asymmetric minimums that exist, which give the lowest energy, but are not really what you would expect. Because for helium, you would expect that they are like this, which is the case. But for other systems like H-, they will change to an asymmetric minimum. And we have no idea why that happens. And we're also still trying to figure out exactly at what nuclear charge this transition from a symmetric minimum to an asymmetric minimum happens. And another point is, for example, helium, for lithium, you would expect maybe the electrons to be distributed as a triangle around the nucleus. However, this is not the case, because the lowest energy, which you can calculate, will have 1 electron at the nucleus and the other 2 further away from it. And this is a bit counterintuitive, because you would expect that the lowest energy solution would be some triangle, but this is the one numerically that gives the lowest energy solution. And we have no idea why it does it, but that is what the science tells us. So now we want to generalize the next 2 order terms, which are these lambda 1/2 and lambda 3/4. And we can do that by using this ansatz of this Hartree project of 3D normalized spherical functions, which have these lambda to the power 3n2, where we put n to 1/4 in the end to have the correct scaling, but we want to keep it as general as possible until now. And we can calculate the kinetic energy, where these are now this different minimum, where we are not expanding around the minimum position, which is, we are not responding around 0, but around these R minimums, because we want to keep it as general as possible for multiple minimums for each electron. We can also calculate the electron-electron interaction terms, the first 2 orders, which is again this constant C, but we also have this Hessian matrix now, which we can luckily simplify, but we also have the alpha and beta here, which is just the sum over the 3 Cartesian coordinates x, y, and z. Now the second order can be rewritten as such. Using the Poisson equation, we get the following. The Hartree-Fock density at the minimizing positions. And we can also use this 3D integral, which you can see here, and we obtain these equations, which look very similar already, because we have again the Hartree-Fock density in front of it at the minimizing positions instead at 0, but again, this very familiar term here. And the same can be done for the exchange operator, which looks like this. And when we switch to our coordinate system with the t, we can get a simplified equation where again, these terms here will just result into the Hartree-Fock density, which we can take outside. So we eventually get the following results all together, and which contains the kinetic energy here, the J here, and the K here. I'm maybe going a bit quickly, but maybe we can look back at the hydrogen atom and you see that it looks very similar to each other. For example, the first 2 terms are the kinetic energy. The second term, which has this 1/6, and then the density in front of here, which is now here scaled in the P, but they look very similar. And here we have both the K here and the K here, which are again very similar with the density in front of it, which is again in the P, and also this factor 1/2 of the s orbital, because here we're using factor 1/2. So if you fill in s is 1/2, we can get that the optimal solution is just the 1s orbital. If filled in is just the scaled version of this 1s orbital. So this is the optimal variational solution for these kind of systems. So this is how we can generalize the equations, where we have here instead of the sum of the Hartree-Fock orbitals at the minimizing positions, instead of just having the Hartree-Fock density at 0. And here we only need to look at the one at the nucleus, because this is only a term important due to the cusp. So this is why we only need to look at the position of the electron at the nucleus. So to summarize it, we have the following set of quantities, as you can see here, where we have now these variational gases, because this was only true for spherical functions that are uncoupled at only the 2 electrons or the multiple electrons. However, for normal systems, this is not exact, so they are just variational gases for us. So our perspectives until now is that we need to obtain W lambdas for larger systems, for example, particles of spheres or the helium isotronic series. But we also need to find these interpolation schemes for the Moller-Plesset Adiabatic connection. And furthermore, we also want to find these DEA expansions, which we have done with Arthur already, for these 2 or 3 terms of the expansion. So let's do a quick dive into the latter 2. So in DFT, there are multiple reasonable interpolation schemes in both limits. For example, the one that's the most simple one to plot here right now is the SPL, which looks like this, which has this square root in the bottom, and also has these constants that are fixed in such a way that they reproduce the correct limits at a small lambda and large lambda, although SPL only does the first order term. And all these ingredients are orbital dependent, and in DFT they are density dependent. So these functionals using Hartree-Fock densities in DFT work very well for the non-covalent interactions. For example, if you look at these 4 different interpolation schemes, they give a low mean absolute error with a very low variance as well, much better than, for example, MP2 or these double hybrid functionals for the S66 data set. And the same can be said for these dissociation curves, where again, we improve with our ISI Hartree-Fock really well on our MP2. You can see that this really improves compared to the reference data, and it's much better than these P2 P-leap, which is the green one, and these localized Hartree-Fock in yellow. So a good step is now finding these interpolation schemes now instead of for the DFT one for the Hartree-Fock adiabatic connection. And that's what we have been looking with Stefan recently. So we can calculate these non-covalent interactions because these functionals used to have a problem with size consistency errors, but Stefan found a way to do it also for non-degenerate fragments, which you can see later on we have solved. So our new scheme is called SPL2, which is named that because it uses 2 SPL-like functionals, which you can see here and here, instead of just 1, because the difference between 2 convex functionals might have this change from concave to a convex function, because it doesn't have to be necessarily convex anymore. Then we fix CB and M1 to the correct large lambda limits, giving us the following constants. And then we use this W alpha beta to get it in this form, because this gives some extra freedom for the W infinity limits to give the correct values and also includes this next order term, which we cannot include normally as well. So this just gives us an extra freedom. And then we are left with 4 fitting parameters, which we are optimizing on the S22 data set. However, more interestingly, Paula came up with a different function, which is used by directly approximating the EC instead, so the correlation energy instead. And you can see the interaction correlation energy, to be precise, and this has the following form, which now has this square root and this 4 square roots, which might be interesting for some of you, because these lambdas can now, as Mike mentioned, also have become complex or be in the complex plane, and maybe there's some interesting way to make these interpolations better using the information we can get from the complex plane. So we can now find again the fitting parameters to give us the correct results. Then in this case, we can fix alpha and beta to 1 because it gives very accurate results already. So we are just left with 2 fitting parameters. And the biggest advantage of this formula is that it has the correct large lambda behavior, because it also has this 3/4 term, in the derivative of this function. So to have the results already for this, we can get the following 4 graphs of the 4 dissociation curves. And you can see here that in green is SPL2. In black, you have the accurate reference data. In blue is MP2. Double hybrid is in purple, and then NF is in gray. And you can see that SPL2 in all 4 of the curves is very accurate and close to the coupled cluster triples perturbative reference data. Whereas the other methods, for example, MP2 or normal SPL, have some problems, and also B3 lib with the D3 corrections from Grimme cannot approximate helium at all. So we have not plotted it there. It also seems to be worse for this system, and is especially bad for these charge transfer states, where even adding these D3 corrections will actually make the normal hybrid worse. And the same is true for this double hybrid, which is again a lot worse for a lot of these dissociation curves. Whereas our NF and SPL give very accurate results using the same computational power as the B2P leap, because the MP2 is the most expensive part of our interpolation schemes, but gives a very high accuracy without using these strange dispersion corrections, and also having always the full amount of MP2 added, not this fractional amount of exchange which the double hybrids have. This can also be seen in these overall results, where we see that these mean absolute errors of SPL2 and NF14 are very low for all data sets. Sometimes B3 lib D3 is better, for example, for S22 and S66. But for L7 and especially DY6 and the charge transfer states, you can see that SPL2 and NF14 are much better than these D3 corrections. So without having these empirical D3 corrections, we can have a very good functionals fitted on one set of data, S22, for a multitude of different non-covalent interactions.
Hey, Tim?
Yes?
So do you know why L7 is so bad for NF14? It seems to be much larger, the error.
We are not sure why it's a lot worse. Yeah, we have not looked at it, why it's okay. Yeah, because it's just fitted on S22 data, we have not really an idea why it would be really nice if we can get our parameters that we now fit exact, so that we can really understand it more clearly why something is bad. It's just now, yeah, I don't really have a reason why NF14 doesn't work for L7.
What is L7?
L7 is a large data set of molecules that have more these, yeah, how do you call it? If these large carbons, graphene sheets that have interactions with each other.
Yeah, layers of 2-dimensional layers on top of each other.
Yeah, and these are larger molecules because most of these sets have always very small molecules, and now they want to also test it on larger molecules, so that's why we have L7 also added.
Macro molecules.
Yes.
And NGD8, what is it?
That's a noble gases. Those are is one that Stefan came up with, which includes like helium, neon, krypton, argon, and then some noble gases with other molecules, small molecules like NH3 or hydrogen.
In the previous slide, because it was really fantastic that you said is the empirical data, the empirical parameters are fit to S22, but it works better for this first data set. But then in this slide, you see that actually helium, am I reading it
yes.
correctly?
Yeah.
So this is not.
Yeah, NF14 is not really good for helium, sadly, but SPL2 is really good for it. And these D3 corrections are even worse. They go up and then they go down and then up and then down again. So we have not included it because they seem to have problems. But I think what Stefan said is that these D3 corrections are known to be not really good for small molecules because they are fitted on empirical data for larger molecules. But yes, you're right that NF14 is not really good at this helium-helium dissociation.
And helium-helium is still in the set for which N14 has the best performance.
Yes, but then it works for the other 7 better because
yes, so it's cancelling. Okay, thank you.
But helium-helium has a very tiny binding energy, so the error is basically swamped by all the others.
Yes.
You see, the relative error is quite large, but it is in the 0.02 kcal, whereas the others are in the kcal regime. Well, I don't know about the other noble gases actually.
Yeah, but helium is relatively small, yeah. So
it doesn't add much to the total error.
And Tim, just to know, so what's the basis set that you use here, and what's the black curve? What level of theory is it?
It's coupled cluster single triple CCSDT perturbative triple. So I think that's the golden standards in wave function based theory. And for the basis set, I have Eduardo does the calculations, so he is the mastermind me all the calculations, but I think I can try to look it up in my emails. But
no, just to know, because the helium-helium like binding curve should be massively dependent on the basis set.
Yes.
Okay.
I think he has tried a lot, and he's also found that, but I think he says that our results are very accurate, or at least he thinks they are well converged. So I think he uses the correct base set, but we will need to ask him for exactly always input data.
Okay, thanks.
Yes.
Yeah. Maybe well, it's not about these results actually. It's a bit back.
Okay.
But this 3/4 terms, this may be interesting to maybe emphasize that you only get that when there is one of these minimum positions is at the nucleus. So for example, in helium, it would drop out.
Yes.
Well, and when you would reduce the charge towards H-, then suddenly when you end up with one of the electrons at the nucleus again, it would pop up again.
Yes.
No, it's not exactly at the nucleus. It's asymmetric minimum, but not with one. It's just that you have one and 5, but not the nucleus.
Of course. Well, okay, it makes sense. Yeah. So for lithium, you would.
For lithium, yes, it looks like one is at the nucleus. Yes.
It's not exactly at the nucleus, but we don't know if that's a numerical error, if that's. But it's also for other larger atoms. We have seen that they always want to at least put one electron at the nucleus. Like for beryllium, you get the same thing. It will not be like a square, but it will just again put one electron in the nucleus and then distribute the other electrons at the lowest position. And also for neon, it will not be in one plane, but it will be 3D. But again, it will always have one electron close to the nucleus. So maybe that's because of this 3/4 term that lowers it, but we still need to look at it more clearly.
And the rest seems to be always kind of a circle around it then, or it can also have a weird.
Yeah, you would expect then for neon that would be like octahedron or whatever, but it's also very strange. You cannot easily get a good structure. It's just gives you something and you need to work with it. That's
this classical problem. I think it's known to be quite erratic solutions.
Yeah, because it's a crystal inside this -R3. And if you, for people like us who have looked a lot at SCE in atoms, it always looks like you have selected at random one of the SCE positions. So it's one of these strange crystals, yeah. But there is no seam. Yeah, except for helium, I have not seen any symmetry. Yeah.
Okay, so then we only have the last part left, which is these GEA terms, which I will now go quickly over, because in most of the calculations, we've always used the PC model to calculate the DFT lambda at infinity. So the W infinity DFT, we calculate using this PC model, which you can derive by using the idea that the electrons are at a strictly correlated position, so they don't have kinetic energy. As Mike mentioned, they only have interaction. So they are at their strictly correlated positions, and then you can divide the whole space into spherical cells where the positive background charge is spread out over the whole density, and the cells around the you can put the electrons in cells where the positive charge within those cells is exactly cancelled by the electron that's within it, which gives us the LDA part, which this term, and then the GA part comes from the dipole moment, which you want to counteract by not putting the electrons in the center of the shell, but slightly away from it, as you can see here. This creates the GA expansion, gradient expansion term. So what we have always used is this inequality, which was proven in the paper already, where we have this DFT, where we use the PC model for W infinity, and we add the exchange, which here we had an alpha and a beta to allow this to be different. However, we know from the exact derivations that this holds exactly, that this WPA, the W infinity of correlation energy of the Hartree-Fock or the Moller-Plesset Adiabatic connection is exactly this electrostatic energy plus the exchange energy. So what we are now going to do is fit this electrostatic energy using this PC model form, where we know that the scaling will stay the same. So we can use these same functionals as you can see here. We also know from scaling that the A of DFT needs to be A equal to the A of this Moller-Plesset Adiabatic connection. So we know this integral with the A, we know this part, we can calculate the integral of that, and then we can just fit the B to the exact data which we can calculate for ions and atoms for this one. So that's exactly what we have done here. We have chosen to fit it on Z infinity, which is what you get if you have a 2-electron system and you increase the nuclear charge to infinity. We fit that data and then plot the B which you get there from, and then plot it for all different atoms. And you can see that the relative error is very low, but also that is for all the electrons and all the systems it work really well. So we just fit it on one data, we get a B from that, and then we look at how good it is for the other electrons. We also use this modified PC, which is from Constantine, which has this following form here. And again, fitting this on the Z infinity so that the relative error is 0, you get this improved version, which has a very low relative error as well. So you can see that using a fitted B, we can get really accurate PC model approximations for this electrostatic energy. And this allows us for relatively cheap to be able to calculate the W infinity C's for the Hartree-Fock system. Then a similar tactic which Arthur has used for the W1/2 for Hartree-Fock is by using this again, and then again using the exact data which we can calculate for W prime, which is in the Hartree-Fock W1/2 for this model. Again, for scaling reasons, these functional forms will stay the same. However, the C now needs to change to this epsilon from the 1/2 system, which gives us the following energy. So we again are only left with D to be fitted to the Z infinity data, which we can do, as you can see here. And we see again that the blue ones and the yellow ones, which is again this modified PC, are fitted on the Z infinity and also give a low relative error, although this is slightly higher. And this might seem troublesome, but you need to remember that the guess, the variational guess that we had was already, a guess of a variational ansatz. So there might be, already the exact data are not really exact, they are just a guess. So that these have a higher relatively error can just be constellation of errors or problems. So this still gives us a relatively cheap way to calculate also the next order terms at large lambda, and allows us to also include these in the fitting, or at least in the expansions. So the outlook is that we want to improve those and also want to have them for the next order term, so we can also calculate them relatively cheaply. And then we want to find new interpolation schemes that use the exact properties from both limits fully. So not like where we have now, where we have these fitting parameters, but we want to have them fully to use. Then we also want to have less or no fitted parameters at all. So we have just theoretically sound models without having to change the fitting parameters. Then we also want to calculate these ones for not only the interaction energies, but also the total correlation energies, because when you plot the SPL2 functionals for the total correlation energies, they are terrible. And the reason why they work so well for the interaction energies is because of the cancellation of errors between the total correlation energies of the complex minus the ones from the fragment. So both are terrible, but the difference between each other is very good. And lastly, we still want to have this change of concave to convex curve, which is especially important for these total correlation energies. So that was the presentation.
Yeah, thank you, Tim. Further questions that you have?